Okay, team, this is going to be a short video which goes into the chemistry of alkynes, namely addition reactions. The reason why this video is going to be short is because the way that alkynes react is identical to the way that alkenes react. So this is a really easy chapter to learn the reactions in. The reactions are exactly the same and follow the same rules as alkenes. So you want to think addition when you see alkynes, and you want to think that they react similarly to alkenes, which I'm going to show you in this video. So remember, hydrohalogenation is reaction of HBr or HCl, and remember that these go according to Mark's rule, as we're going to see. Hydration is reaction of water, usually with an acid catalyst. This also follows Mark's rule. Hydroboration is basically, through a complicated mechanism, it's the addition of water, but anti-Mark, remember. And halogenation is going to be Br2 across the pi bond, and notice that since it's the same atom, you don't really need to worry about Markovnikov's rule. Okay, so first let's look at hydrohalogenation. Let's say you have HBr, you add it to an alkene. Remember that the bromide ion goes to the more substituted carbon, the hydrogen goes to the less substituted carbon, so you get a hydrogen on the less substituted carbon, you get the bromine on the more substituted carbon. So let's say we add HBr to a terminal alkyne. Well, the intermediate that we're going to get is this one, where hydrogen went to the less substituted carbon, bromine went to the more substituted carbon, but we still have a pi bond and we still have HBr present. So notice that we're going to add HBr twice, once across each pi bond. So we're going to get two HBrs that added to the alkyne. The two bromines are both going to go to the more substituted carbon, and the two hydrogens are both going to go to the less substituted carbon. Remember from the previous video, this is called a vicinal dibromide. So the addition of HBr to an alkyne gives us a vicinal dibromide where both bromines are on the more substituted carbon. This is convenient, right? Because we can take an alkyne, we can add excess HBr to get a vicinal dibromide, then we can eliminate it to get back the terminal alkyne. So depending on which direction you want to go, you can go from alkyne to dihalide or from dihalide to alkyne. This is an addition. This is an elimination. This is exactly the same as what we saw with alkenes. Okay, so things get a little bit fuzzier when we start to hydrate, because remember that if we take sulfuric acid and water and we add it to an alkene, the OH goes to the more substituted carbon, according to Mark's rule, and the hydrogen goes to the less substituted carbon. In the case of an alkyne, we need to add a mercury catalyst, but what we end up with is this product of addition. It turns out, for reasons that we're going to talk about next semester, and I'm not going to go into the mechanism of this, that these compounds are called enols, and they like to rearrange to form a carbon-oxygen double bond. So notice here you have a carbon-carbon double bond. It rearranged to make a more stable carbon-oxygen double bond. Essentially, what happens is the pi bond moves here and the hydrogen moves there. That's not actually the mechanism. We're going to talk about the mechanism next semester. All I want you to know is that the oxygen ended up on the more substituted carbon, and the hydrogen ended up on the less substituted carbon. We still added water across the pi bond. It just turned out that the two hydrogens ended up on the less substituted carbon, and the oxygen ended up on the more substituted carbon. So just to kind of recap here, the way you want to think about an alkyne is that you have a carbon-carbon triple bond. If you undergo hydration with sulfuric acid, water, and this mercury catalyst, then you get this double bond to oxygen on the more substituted carbon, just like we saw in the past. The oxygen goes to the more substituted carbon, and the two hydrogens of the water molecule end up on the less substituted carbon. This hydrogen was there to begin with. This is called a ketone. Alternatively, remember, we could hydroborate. That would give us a hydrogen on the more substituted carbon and our oxygen on the less substituted carbon. So as you can see, the oxygen ends up on the less substituted carbon and the two hydrogens end up on the more substituted carbon. This is called an aldehyde. So hydroboration oxidation gives us an aldehyde, whereas hydration with an acid catalyst gives us a ketone. So in this case, notice, same thing that I just showed you. Hydration with an acid catalyst and a mercury catalyst gives us a ketone. The oxygen is bonded to the more substituted carbon. Hydroboration oxidation gives us an aldehyde. Generally speaking, there's sterically bulky groups that are placed on this boron. If you put BH3, that's fine with me. There's some other examples that are listed in the textbook, like dicyclohexyl borane. Okay, so remember, if you have an alkene, that bromine will add across the alkene to give us a dibromide, and that this bromination reaction gives us the trans dibromide. If you have an alkyne, just like we saw with HBr, it's going to add twice. So first, you're going to get your dibromide with one pi bond left over. That will undergo a second addition reaction. So you get 4 bromine atoms, just like we saw with hydrogenation. You get 4 hydrogens. Here you get 4 bromine. So bromine adds twice. Since you have 2 pi bonds, they both undergo an addition reaction. All right, so I said this was going to be a short video. What we talked about actually in the last video is that you can reduce alkynes to give alkenes, cis alkenes, or trans alkenes, depending on the conditions. What we saw in this video is that you can add HBr, and that follows Mark's rule. You can add bromine, and that gives you tetrabromoalkanes, which just means it adds bromine twice across the 2 pi bonds. Hydration produces ketones because the oxygen goes to the more, so the double bond to the oxygen goes to the more substituted carbon. Hydroboration gives us an aldehyde because the double bond O goes to the less substituted carbon.